Today we start our 11th week of classes. So we have four weeks left until the end of the semester. We are almost. I think I'm going to finish and start the new chapter today. We only have the structural alignment problem to discuss today, and we will finish protein structures. And then we are going to start talking about gene expression analysis, and we are going to only look at the clustering problem in gene expression analysis. I'm not going to talk about different. I will talk about in general about what differential expression is, but I will not talk about methods for identifying differentially expressed genes. And after that, we're going to start talking about biological networks, and with that, we're going to conclude our semester. So I also, you must have received emails about email announcements from Oticlas about the assignment, the third assignment, which is analyzing a protein structure and finding its diameter. Basically, this assignment should not take more than an hour of programming. It's just reading a text file, just getting the necessary information only by ignoring some of the lines in the file and getting carbon alpha coordinates and just finding the farthest distance between the carbon alpha coordinates and printing out information about between which carbon alpha atoms this distance is obtained. Okay, so, but it should help you to understand the structure of a PDB file, how you parse it, so it will be some programming exercise for you. You may use any programming language you want. You may use a library, for example, which parses PDB files automatically and get the coordinates, but you should be careful in using an existing library like that. For example, you should be able to specify the parameters to tell you that you get only carbon alpha coordinates. For example, if you just read the PDB file and the coordinates are in some array, and if those coordinates include all of the coordinates of the atoms, then you will be computing the distance incorrectly. Okay, so if you use a library, it's free to use such libraries, but just really, what I'm asking is very specific. Just make sure that those libraries support such specific queries, or maybe you may need to post-process their result or whatever. But the easiest case is if you write the entire program from scratch without using any library, it's not a very difficult program to write. I mean, parsing a text file and checking whether a certain characters in certain columns of a line is carbon alpha, then reading the rest should be easy, and just put them in an array and run. You don't need to be. I'm not asking you to find an O(n) log n solution, which may be possible to find the diameter of a point set in O(n) log n time, but you don't need to do that. Okay, a quadratic solution which runs in O(n) squared time, which is the exhaustive search of all possible pairs of carbon alpha atoms and maintaining the maximum distance, works really fast in these protein structures, even the large one. Okay, so we are not talking about trying to find an algorithm that can find the diameter of this point set in O(n) log n time. Although this is possible, okay, there's the efficient way to compute the diameter of a point set can be done in O(n) log n time. First, by computing the convex hull of the set, and then after you have the convex hull, you can process the convex hull in linear time using an algorithm named rotating calipers algorithm, which will give you the diameter of any convex polygon. But I don't want you to do that in this assignment. This assignment is not that complicated. Just you can have the quadratic algorithm, which runs in O(n) squared time, which checks the distance between all possible pairs of carbon alpha atoms and report the maximum one. And I also check that the output amino acid pair is unique on all of these protein structures, which means that there is no equality between two possible pairs. So it doesn't matter where you're looking for the maximum, whether you use greater than or greater than or equal to, it will always give you the same pair of amino acids. Any questions about the assignments after my explanation? Okay, so I hope it's clear. And
Thank you, sir.
yeah, so if it is, if you have any questions, feel free to email me anytime. All right, so let's continue with today's topic, which is again about protein structures. And it was the methods now I'm going to talk about are to find given two protein structures, for example, this one and this one. How structurally similar are they? Maybe as globally as you can see, these two are not similar, but maybe a part of it. For example, if you look at this chain here, it may look similar to this one. So finding some similar substructures. So we're in structural alignment, we're necessarily interested in a local structural alignment. We trying to find local structural shapes that are similar to each other in terms of shape. And if I say, for example, this one and this one is similar to each other, first, the most difficult problem is identifying, matching those parts, the association of amino acid. This one matches this one matches this one. Since it's an alignment uh, problem, again, we have to do a one-to-one matching of amino acids with respect to each other. One thing that you may have different in structural alignment compared to sequence alignment is that there are structural alignment programs which do not take into account the sequence order of amino acids. For example, when you match amino acids with each other in sequence alignment, you cannot have crosses like this. For example, an amino acid that is here is matched over here, and an amino acid that is here is matched over this. Cannot happen. So we have to, in sequence alignment, the sequence order have to be preserved. But in structural alignment, there are some programs which actually ignore sequence order and just focus on structural similarity and trying to match structures by just using shapes. So there may be different order of amino acids in one of the structure you find. I mean, if you follow the linear three-dimensional curve, uh, the alignment may match amino acids that are like this on the structure in structural alignment programs, because we're just interested in the shape. We may just treat those carbon alpha atoms or the coordinates of the amino acids as uh, independent three-dimensional coordinates and ignore the order, the peptide chain, which has a certain order like a three-dimensional curve in 3D space. So there are both ways. So when you're, for example, using a structural alignment algorithm, if biologically you're interested in alignments that preserve sequence order, you have to really look at the method, description of the method, where it should say someplace that it's either preserves sequence order or not. Okay, but most of them are local structural alignment programs. They try to find local shapes, and here we are trying to optimize two things which are actually in conflict with each other. They compete. So here is we want to find a structure, similar structure, which is as large as possible. So usually when we are given a structural alignment, we are given two things, two measures as to how good that structural alignment is. One of them, the first is how large the substructure, similar substructure you have found. Is it the first thing is the length of the alignment, how your local alignment, how many amino acid matches you have in your structural alignment, its size, the size of the similar shape you have found. That's one thing. And the other is how similar, when they are superimposed on top of each other, what is the root mean square deviation between the matched amino acids in the structure. So it's basically these two, length and root mean square distance, are two things that you look in a structural alignment result. And as I said, these are competing with each other in the sense that you may get a very low RMST by just matching a small part of the structure. For example, you may match a triangle, a triple of amino acids here to, there may be another triple of amino acids here, and we may get a perfect match between them. If you superimpose them on top of each other, you may get the perfect match in which the RMSD is very small. Maybe it's zero. Okay, RMSD, we compute RMSD after somebody gives us which amino acids are matched, and we superimpose those matched amino acids onto the other, in one protein to the other protein. We compute this RMSD value after the superimposition by computing the distances between matched ones. So as this formula says, first compute the distance, take the square of these distances, so it's squared distance, and take the average mean square distance. Take the average of those square distances and take the square root of that finally, which will again be after this square distances, their unit is angstrom squares. By taking the root finally, we get it back to the angstrom unit. So RMSD here may be zero. So it's very good. Smaller the RMSD, the better the alignment. Okay, it means that those shapes are really matching. They're on top of each other. But here the length of the alignment is fairly small. I mean, it's just 3 amino acids. We usually measure the length with how many amino acids you have matching in your found structure. So this 3 amino acids and the RMSD of 0, it's really very bad. And by actually some methods combine these two measures into something else by providing a statistical significance measure. For example, okay, you have found an RMSD of 0 with 3 amino acids. How significant is this result? Probably not significant, because between two unrelated, completely structurally different proteins, you can still find an RMSD of 3 angstrom and 0, so length of 3 amino acids and RMSD of 0 angstrom. So between two really structurally unrelated proteins. If these, even between unrelated proteins structurally dissimilar, you can find the chance of finding the same alignment is high. This means that this alignment result is not significant. Okay, therefore we may compare these against a random null distribution of bad alignment results, and here this may be one of those bad alignment results you get between two structurally unrelated proteins. So as I said, these are two competing measures. When you increase the length, RMSD also tends to increase because if you include more and more amino acids in your alignment, the new parts that you introduce, it will make it difficult to match the structures. The structures is going to start deviating from each other in terms of shape as you increase more and more amino acids into your alignment, and therefore maintaining a low RMSD will not be possible. But if your structures are really similar overall in terms of shape, you will be able to find an RMSD of like maybe 2-3 angstroms RMSD and an alignment of maybe 200 amino acids. So such a result, for example, is really saying that there is a big part of these proteins which is composed of 200 amino acids. I was able to match 200 amino acids from one structure to 200 amino acids in the other structure. And if you align this 200 amino acid part, if you superimpose these 200 amino acid part on top of each other, the root mean square distance between them is 2-3 angstroms, means that it's really almost on top of each other, only small deviations here and there. So an RMSD value of 2-3 angstrom means that the structures are really similar to each other. If your RMSD increases to 7-8 angstroms, the structure there, it means it's not that, the structures are not that similar. Okay, so we are looking for good alignments which gives us maybe 2-3-4 angstroms at most in terms of structure, in terms of distance between average distance between the matched amino acid pair. Now, so that's a really nice challenging computational problem. which also attracted my attention after during my PhD. This was the next problem I attacked after I started protein visualization. So visualizing a PDB file is not that challenging. I mean, you just provide some. You can do it in OpenGL really easily these days. You have this hardware accelerated graphics cards and GPUs. You can visualize large structures differently, but there are still some research areas, even in visualization, like how do you compute the molecular solvent accessible surface and compute the electrostatic potentials on the surface of a protein structures efficiently is still maybe one of the research problems, but just visualizing them was not that interesting. So this structural matching problem attracted my attention, and I said, "Oh, this is nice. This is a nice computational problem. Why not I read more papers about this and try to find a solution?" And I also had the advantage of having an advisor who was an expert in computer vision, and his main expertise was in shape matching. Okay, so shape matching, but three-dimensional geometric objects like these. Trying to search, for example, if you give an object like this, try to search similar objects like this in an image database. So you have to find, this is a shape matching problem in general in computer vision. But as you can see, the structural alignment problem is very similar to shape matching. So that's why he was able to propose some methods that he used in shape matching and I was able to implement some of them, adapt some of them to this area of protein structural matching, and we also developed an algorithm for this purpose. But it was the first thing you are going to see that is you have to, in shape matching, for example, you have to extract some translation and rotation invariant features. You cannot just use the PDB coordinates and try to find similar looking PDB coordinates in the other file. So you cannot try to directly align PDB coordinates, turning those numerical values into some scoring scoring values, whether they match or not. The coordinates of a PDB file here is really, as I said, irrelevant in terms of the coordinate reference frame. Each of these protein structures are obtained, may be different, and the XYZ values that I have in the PDB file, their locations, they're really not actually important. The relative positions of these amino acids between each other are important. So what I mean is that if I move this protein anywhere in 3D space and if I rotate it, it's still the same protein structure. So therefore I need to extract translation and rotation invariant features, which means that you have to extract things that are not changing. Translation rotation invariant means when you translate it and rotate it, whatever measure you compute for that protein structure to summarize its shape, it doesn't change. And one of the algorithms that I'm going to describe to you right now is called DALI. And the DALI algorithm uses what can be rotation. So they thought about what can be rotation invariant. If I give you a protein structure as a three-dimensional linear curve like this, for example, if this is the N terminus, this is the C terminus, and I have a protein structure which may be like this. Okay, so this is the order. This is C terminus and N terminus. It goes like this. So if I have this shape, very, very good. Well, choosing a pivot atom. For example, you can choose a pivot atom and then use it as your origin, right? If you use it as your origin, just the pivot atom gives you an origin, but you have to also choose your XYZ axes because you still have some 3 degrees of freedom in terms of rotation. Uh, for example, in your assignment, you will be computing the diameter of the protein structure, right? If you translate and rotate the protein, does the diameter change? No, right? It shouldn't change. I mean, if the distance between the farthest atoms is, for example, 100 angstroms, if I rotate this, move it around, I rotate it, it's still 300 angstroms between the farthest atoms, right? So one thing that is preserved, but one thing that is translation rotation invariant is the distances between atoms, and that's what the developers of the DALI algorithm realize. Also, many algorithms use this feature. Not only DALI, there is an algorithm named combinatorial extension. So these are the first, maybe they were the first papers I read during my PhD when I started talking about how to find a method for structural alignment. So C is combinatorial extension, and they're developed by researchers from UC San Diego. And DALI is also a famous method. So DALI structural alignment. So these are the, so they have a server, DALI server now. So I think in Wikipedia they also talk about the history. Oh, look at this. This is a nice superimposition of two protein structures. They are really, but even they're almost completely identical. There are certain differences, right? So here the differences, the standard, it means that the RMST is not exactly zero. Maybe it's 0 0.1, 0 0.5, but it's still, they're really nicely matching. So let's take a look at does it have an history, where when was it, so it just talks about the methods, structural superimposition, algorithmic complexity, structural alignment, methods. So it talks about the methods. So it's wow, this is a really, oh, as you can see, when it talks about methods, so it's about general structural alignment methods. Oh, okay, this was not a DALI page. I thought it was just specific to DALI. So as you can see, under the methods section, the first two methods they mention is, the first one is DALI, the second one is C. So they are therefore also for me the first two algorithms that I learned. I don't know the details of the Mammoth algorithm or SSAP, is sequential structural alignment program. Well, actually, I think double dynamic programming. Oh, so this is no, I'm not going to talk about SSAP, but an algorithm that is similar to that. And there are some recent developments. If we go and click on, so this is the DALI paper by Holm and Sander in 1996, mapping the protein universe. And this Shindialo, Philip Byrne, and Ilya Shindialo, I had a chance to meet them as well. So they are developers of the C algorithm in 1998. So as you can see, when I started my PhD in 2000, it was in those days, these were recent algorithms, and I was just trying to find uh, some unsolved part in this problem, like maybe trying to do, instead of doing pairwise structural alignment, can I extend this method, for example, to a database search of structures if I find a fast aligner? These were both DALI and C methods. At the time, they took a couple of seconds for a pair of protein structures to align. So it was, they were not really fast, but they use, I'm not going to talk in technical details of these algorithms, but just want to mention to you that what kind of structural features that they use. Uh, DALI uses what we call intraatomic distance matrices. Intraatomic distance matrix means that between every atom here, if so, just like the idea of choosing a pivot, which one of those are we going to choose a pivot? Why not fix a pivot? Compute the distances between every pair of atoms here. And when we are doing the structural alignment, actually, we have to decide on certain things. for our assumptions. For example, are you going to use all the available atoms? What if one structure have hydrogen atoms in it, the other does not? Or are you going to use the locations of the side chains? At which level? Or are you going to do the alignment? For example, are you going to represent the structure as a set of atoms, alpha carbon atoms that we do in our third assignment? Or are you going to look at the secondary structures and maybe represent the entire protein structure as some secondary structure vectors like this? Okay, there's a helix here, there's a beta strand, there's another beta strand here, there's a helix, there's another beta strand. You may have a more higher level of structure looking at those structures. Maybe just I'm not interested in individual atoms here. I know that there's a helix here as a like I can represent this helix as a line segment oriented in certain direction, same as beta strands. Maybe when I'm doing my alignment, I should not really care about loops that connect these parts. Therefore, just representing the entire structure as a collection of uh, line segments that represent the secondary structure and their orientation. By the way, some of the, just having line segments may not be a good way to represent all the secondary structures. As you see this figure here, these beta strands, they may be slightly curved. You may approximate this as a line segment like this, but maybe representing it as a curve is also possible. But one thing that we should decide on is how we represent these structures by its atoms, by its secondary structures, or something else. So Dali and C, they both represent the atoms as a list of atoms. If I maybe the original method in both of them, the original methods probably just take a look at the carbon alpha atom. So each amino acid, we don't want to go into too much detail and look at all the atoms: nitrogen, carbon, the other carbons, the side chain. In the simplest case, a protein structure is the representing the protein structure in the simplest case is by using its alpha carbon, the carbon alpha trace, which means that for each amino acid, I'm going to use a single XYZ coordinate to represent it. Again, just like in our third assignment. And this is what CE does. And I think Dali also does that because the size of this intraatomic distance matrix is whatever the number of amino acids a protein has. We are going to have an n by n matrix if the number of amino acids it contains is n. It means that every amino acid is represented by a single coordinate. It may be this central atom alpha carbon is like a central atom for that amino acid, and using its coordinate does make sense, and it gives us a piecewise linear curve. If you connect each consecutive alpha carbons with a line segment, it will look like something like this: alpha carbon trace. If you look at images like these are, yeah, this one. Look at this. So this is the alpha carbon trace for two structures. It's still really complex. As you can see, if you zoom in on this, it's just a collection of line segments. It becomes like but a collection of those like this, it makes them a three-dimensional curve, which are piecewise linear. So between every alpha carbon, I have something like a line segment between them. It's possible to use not linear curves, but given these three-dimensional points, you can have like cubic splines. There are higher dimensional curves in 3D space, which you may interpolation splines. You may use splines to have a more smooth curve that pass through all these points. Okay, but in any case, we're going to be using the curve is going to pass through some knots, which are the position of your carbon alpha atoms, and our goal will be to find their structural match of these two curves. So DALI starts with uh, computing this n by n intra-atomic distance matrix. So it's something like this. Let's have an m by m matrix in which this is atom 1 or amino acid 1, amino acid n, amino acid 1, amino acid n. All right. So actually, yeah, 1 and n could also be here. Okay, 1 and n. So this is 1. The distance between the first amino acid and the first amino acid, what is it? It's 0, right? So the diagonal will be all zeros because it's the distance of the carbon alpha atom to itself. And this matrix is going to be symmetric because the distance of the ith amino acid's carbon alpha to the jth one is equal to the jth to I. So it's a symmetric matrix, and we can actually have, for example, whatever the distance between ith and jth carbon alphas, we can write this as a numerical value here. There is also a way to visualize those. Let me show you a visual. So I'm going to talk about that method. Yeah, look at this. So this is the intramolecular distance matrix for myoglobin, which contains around, I think, 142 or 140 something amino acids. As you can see, it's a square matrix, 142 by 142. And the way the rows are arranged, the one is here. So from the first amino acid to nth amino acid, so it put the first amino acid here. So the diagonal we have goes like this. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and it goes 142, 142. And the numerical values here are coded in grayscale to visualize that matrix with an image like this. And you can imagine that the distance of 0 is mapped to a black color because we have a completely black diagonal here. We know that the diagonal is all zeros. And the maximum distance you have between two carbon alphas, for example, which may be your diameter. So you may, at one end, you have 0. At the other end, you have the diameter of your protein. And you can rescale all of the distances in between them between 0 and 255 in terms of your grayscale values. If your whitish grayscale value, if white is represented by 255, or I mean, if white is 1, you rescale everything between 0 and 1. And when you display it as an image like this, you get this one. Now, let's look at this image. What does it tell us? I mean, obviously, this diagonal is not so much interesting because we expect the diagonal to be black anyway. But look at these off-diagonal entries. What does this mean? What does this blackness mean here in this region? Let's try to, and there's, okay, since this is symmetric, the same blackness should appear here too. Therefore, we can ignore 1/2 of this matrix and concentrate our attention on only this half. And let's see, we have this here, this black region here, and this black region here. What does it tell us?
They are close to each other, sir.
Exactly. They're close to each other, but why, for example, look at these amino acids. If you look at these amino acid number, it says that the amino acids from 0 to 20 or 0 to 40 are close to, for example, the amino acid 0 is close to 130 and 1 is 129 maybe. So it's roughly in 90-degree angle to the diagonal. And these amino acids are, yeah, really these amino acids are close to each other, but can it be some kind of a secondary structure that you can think of?
Maybe. I'm not sure.
Yeah, it may be. What about, for example, think about beta strands. So just think about so what this part say is that from 0 to, I have an amino acids from 0 to 40, they are close to each other. 0 is close to this 130, and the 40th one is close to like 90. Yeah, so it goes all the way. Actually, it's like 1 to 1. So 40 amino acid is close to 90. So there are exactly 40 amino acids in each that are close to each other. So look at this. The direction is here, and the direction of the chain is like this. And these amino acids are closer to each other in 3D space. The distance between them is close. Exactly. This is an anti-parallel beta strand, beta sheet. So two beta strands that are anti-parallel to each other. So this one, if you look at the intraatomic distance, this reveals something. Actually, from here, I think this is the reverse problem. Somebody gives you these pairwise distances. Can you uh, form uniquely what the three-dimensional shape is? This inverse problem, I think, it is also possible to do that. But it reveals certain beta strands here. What about alpha helices? Where should they be? Since the alpha helix is really like a local structure, I think these black areas closer to the diagonal. So the diagonal still has some black areas around it. It's like the diagonal is like extended a little bit in certain regions. For example, every in an alpha helix, for example, every amino acid is closer to every I plus fourth amino acid. So they're whatever the alpha helices, whatever they are, they should be around the diagonal anyways, because their relationship with other protein structures is here. And there are some irregular, for example, black blobs around, which may indicate how those alpha helices are related to beta strands and such. But in general, this is like distance matrix that is given to us, and it's a translation and rotation invariant feature. So the Dali algorithm basically given two intramolecular distance matrices of two different proteins. So I will have one for one protein, and I will have another for another protein. So do I have that here? No. I can actually view them all in a single rectangular matrix. I use no, actually, it will not work. So it's a square matrix. I will have one for one protein. Another protein that I want to align it with this one is going to have another intramolecular distance matrix, which may not be the same size. Okay, it may be a 70 by 70 intramolecular distance matrix. And our goal in structural alignment is to find uh, some regions here in these matrices that are similar to each other. So what DALI does is first divides this entire large matrix into smaller pieces and finds smaller matrices that are matching to other smaller matrices of same size in the other one. So all these structural alignment methods, they first start just like BLAST. BLAST has the same idea, right? I mean, first find a good match that you can use as a seed, then try to extend it, try to combine it with other things that are matching. The same idea. If you want to find a nice large structural match, there should be first, in a large, nice structural match, there should be small regions that are very much similar to each other. Okay, overall, the entire structure we will lose certain similarities, but there should be certain parts which are really similar to each other, and that's what DALI starts. It first maybe uh, looks at 8 by 8 matrices here, 8 by 8 submatrices here, and if you find similar looking 8 by 8 matrices in the other one, that those are your matching pairs. And your goal will be to combine matching pairs consistently uh, to reveal larger matching substructures. That's the main idea of the DALI algorithm. The C algorithm is also similar to that. C algorithm, instead of working on a matrix like this, it just it goes over the alpha carbon trace, uh, starting from the beginning. It slides the window of size 8 over so it looks at every 8 consecutive amino acids and computes the pairwise distances between those 8 amino acids. Again, it uses the pairwise distance. So this pairwise distance is a nice way to have an invariant structural feature. Okay, uh, so it slides the window over the overlapping window of size 8 over the entire protein structure and computes this regions, distances between eight consecutive amino acids. And then it finds, it does the same thing for the other protein structure. Again, it tries to find a pair of windows with similar distance values between them, between the two protein structures. Again, this is like a seed. The combinatorial extension, as the name suggests, it tries to first find these seeds. You will have a lot of matching pairs between these two. There may be more than one matching pairs between the two uh, protein structures, and you try to combinatorially extend your match by including different pairs together to form a larger set. So that's the idea in the general idea in combinatorial extension algorithm and Dali algorithm. Okay, so but after we find the matches, let's go back to the slides. And I'm also going to talk about another algorithm in detail, the structural algorithm uses the idea from sequence alignment, dynamic programming, but like an expectation maximization algorithm, it does two things iteratively until we have convergence. We are going to see it. So the SSAP is also mentioned in that Wikipedia article. It was in 1990. And there's so distance-based methods they use look at the uh, intradistance matrices or intradistances between windows, interatomic distances. So these are distance-based. There are vector-based methods that I told you that we may represent protein structures as vectors of secondary structures. This is what WAS does. There's 3D search, top scan in 2000s. There are methods that use a combination of both. Okay, so here, so when we go back to the beginning of this, our goal is in protein structure comparison. And why do we want to compare structures? There may be many biological motivations to find, for example, whether a prediction is correct. If you want to evaluate a structure prediction algorithm's accuracy, we compare the predicted model with the actual model. So in comparison of these things in benchmarking, structural alignment, structural prediction algorithms, we need structure comparison. Another thing is when you get a new protein structure, I have talked about the structural database scope in which all the folds in nature are organized hierarchically like this in terms of shape. One thing that one challenge is when you get a new protein structure, which scope class, family, superfamily, or fold it's going to be a member of, it's going to belong to. Can you identify, given a new protein structure, can you identify its structural fold class automatically? Uh, that's a problem, right? I mean, if you can do that, it may also be used. If you can do that efficiently, it can be used for function prediction too. For example, if you have a new protein structure, after finding the protein structure, if you can find which scope category it belongs to automatically, it will tell you. Also, it will help you to grow the scope database nicely automatically. And to be able to do that, you have to do structural alignment. Find structures that are similar to your new structure. And some of these are a repetition of what I already said. Also, I'm going to skip them quickly. We may do the structure comparison at the atom level, at fragments level, secondary structure element level. So this fragment is like sliding a window of size 8 amino acids. Those are my fragments, 8 amino acid fragments. I can do my alignment at that level. I can represent the entire secondary structures as vectors. And when we are doing the comparison, sometimes we maintain the sequential order of residues or not. Sometimes you're comparing, you don't just compare with respect to geometry, but take into physiochemical properties into account too. You should not align just because they are similar in shape. You should not try to align a hydrophobic amino acid with a hydrophilic one. So you may also take into account this physiochemical properties. So when you're comparing what you're going to consider, you have to all, when you're designing a new algorithm, you have to all consider these things. And the key problem I stated earlier again is to find the matching amino acid pairs in the alignment. Which parts of the structure you're going to ignore there by saying they're not similar, which amino acids will be matched. So finding the match is the key problem. And which we don't know beforehand. This is what we try to find. And there are some issues are the Cartesian coordinates, the PDB, the coordinates we have in the PDB file. As I said, they're just arbitrary coordinates with respect to some random reference frame. We may consider, instead of considering distances, we may consider angles, or you may consider volumes. You may consider that there are many geometric features that are translation and rotation invariant. And some of those which I used in my method, was curvature and torsion along a three-dimensional curve. Curvature is something 2D, which can be computed in 2D. It's between three consecutive, like the dihedral angles between three consecutive carbon alpha atoms. For example, it's this. If you give two carbon alpha atoms, three consecutive carbon alpha atoms, which are oriented like this, the curvature is like the derivative of the curve at in the middle one. So, for example, if I have three carbon alpha atoms that are like this, the curvature is less. As you can see, it's a larger circle passed through them. So the change, the derivative at this point in the middle is less compared to the derivative here. So curvature is something 2D. Torsion, on the other hand, torsion is another term, which is the tendency of the fourth atom. It's between, in order to compute torsion, it's a three-dimensional entity. You have to you can look at the fourth carbon alpha and see whether this carbon alpha atom is close to the plane that is formed by these three atoms. So these three, they form a plane in 3D space, a unique plane. And if this carbon alpha atom is on the same plane with them, the torsion is going to be zero if they're all four of them are linear. But how far it goes above or below the plane in three dimensions, this curve, how far it wants to get away from the current plane of the last three amino acids, tells us, for example, torsion. These are also some features that you can compute which are invariant. These are some also geometric features. And after that, we compare, we try to, by using these features, we try to find regions in those structures in which these computed geometric features are similar to each other as much as possible. And we want to find as large region as possible. And after we do the matching of amino acids, we computing the RMSD is very simple. There's a linear algorithm to superimpose two protein aligned parts on top of each other, and then we can compute the RMSD. So there, I'm skipping these parts. So after the matching is done, we based on the matching, when we superimpose them, the best way to superimpose, for example, if you do the matching incorrectly between different amino acids, superimposition may get you something like this, which tells you that the aligned amino acids, they are not very similar in shape, probably. But if you were to align these parts and ignore, for example, there's a gap. You can also have gaps when you're doing the matching of amino acids with each other. Obviously, you're going to ignore, since this is local alignment, you will have gaps in your alignment. Only certain parts will be matched against each other. And if you use only the match parts to do the superimposition, you will see that these two structures, maybe these parts of the structures may be very similar to each other as they superimpose on top of each other really nicely, and the root mean square distance between the match parts when I'm computing the root mean square distance, I ignore the distance between this part and this part, this part and this part, which are far away, because these parts are not probably in my uh, matched parts, because the distance between them is large when I try to do the superimposition by trying to get them close. As you can see, I mess up the other parts. So the root mean square distance, finding the best way to superimpose, it tries to do something, the best superimposition considering the matched amino acids. And this may be the best way to align them on top of each other if the entire structures, amino acids are matched with each other beginning to the end. But as you can see, this alignment is not good, and superimposition told us that these two structures overall, if you match all the amino acids, it's not good. I mean, this is the minimum RMST we can get, and it shows that it's not good. But if you just ignore, I mean, when you're doing the matching, you say that this part does not match to this part does not. If you have gaps, and if you do the RMST only by considering the matched regions, then the minimum RMST can show you the better minimum RMST, and show you that those parts that you aligned are really structurally similar. Okay. Uh, so yeah, this is the repetition of it. We already told you. I talk about the translation, rotation, invariant features. I also talked about root mean square deviation, or root mean square distance, how it's computed. So we just compute the distances. So the root mean square distance is roughly the average deviation between the matched atoms. So this shows the root mean square distance between these two fragments, peptide fragments. But this, as the figure, this figure, let me just show you. So if this is the distance between 5 and 5, d5, 4 and 4, this is root mean square distance between these two structures as they stand in this 3D space. But let me ask you, is it the minimum RMST between these two structures? When I talk about minimum RMST, if this minimum RMST is can be computed in linear time, provided a matching between those two. Now I ask you let me ask you a question. What you see on this slide, it tells us that this is the RMST. Is it the minimum RMST that is possible between these two structures? Or is the minimum RMST between these two structures zero? Let me ask you two questions. Can the minimum RMST between these two structures be zero? And what you see here on this slide, which is computed by using these dashed lines as the distances, is it the minimum RMST? Can you decrease the RMST between these two structures? This is the same way as asking. You probably can, right? I mean, maybe that's a very obvious question, and that's why you're not. Nobody says no. You should say a big no. This is not the minimum RMST, because imagine moving the green structure down. What will happen if you move the green structure down? Translate it. In terms of structure, its shape doesn't change, obviously, and because you're free to translate and rotate these protein structures, there is no reason why this is very far away from the other. When during superimposition, we are free to translate and rotate. So what will happen when you move this green structure down? The distances are going to decrease, right? So in superimposition, your goal is to translate and rotate in such a way that it is, so it's probably going to be something like this. If you move the green structure as close as possible to this one, it will 1, 2, 3, 5. The green ones are going to be like this. And since the red structure is a linear structure, it will be impossible to have a zero RMST. You're not allowed to bend, change the dynamics. You're not allowed to change the structure by moving atoms here and there, because it means that you're changing its shape. You're only allowed to translate and rotate it. So maybe if you rotate it a little bit, for example, if you rotate it a little bit in this direction, 5 is going to be matched with 5 nicely. Maybe 1 is also going to be matched with 1. But there's a problem. This 3 may go farther away. The deviation may put the distance between these two larger. So, but in any way, the algorithm by Umayama, I think there are two different algorithms which were published in similar times. This linear algorithm, which finds the RMST between two matched point clouds, does this optimally in linear time and finds you the best way to translate and rotate. It will tell you you have to rotate this angle, you have to translate it this much, and this will give you, after the superimposition, you find your minimum RMST value. That minimum RMST tells us structurally how these 5 atoms are similar to each other. If I had the purple one, for example, if there's a purple one which is like this, it's still not entirely linear, but the purple one will get a lower RMST when we try to superimpose this purple over the reds ones. So by comparing the RMSTs, you can uh, talk about whether they're similar or not. Yeah, similar structure RMST is usually in the range between 1-3 angstroms. One disadvantage of RMST is that all atoms are treated equally. If you're not only looking at alpha carbon atoms, maybe you may compute RMST by giving different weights to more important atoms, or whether the atoms are at the core or at the surface. There are different versions of RMST. Um, Significance of RMST, size dependent, is very important. So as I said, without the length of the alignment, by just looking at the RMST, you may not understand whether the alignment is good or not. If somebody tells you that I have found an alignment with RMST 0.1, and it's a very good alignment, you should ask them, what is the length of your alignment? If they tell, okay, my length of alignment is 5 amino acids, it's not very good alignment, you should say. So the length of the alignment is also important. I'm skipping those alternative RMSTs. So since we have started talking about DALI first, let me finish DALI. But yeah, since it's 10:38 right now, it's a good time to have a 10-minute break. I will stop recording now and have a 10-minute break, and after that, we're going to continue with the details of the DALI algorithm.